All right, this is the last day of lecture. Lesson 67 is going to be pretty short about nuclear fusion, and then we're going to talk about biological effects in lesson 37, and then you will be all done, ready for your bonus quiz on Wednesday, your exam 4 on Friday, and then your final next Monday. Okay, so we're finishing up chapter 21. Here you can recap nuclear fission and its uses. Just this is the definition in the previous one, and some of the examples we talked about were dating, medicinal, and then energy. Okay, so those are 3 uses we talked about last time, and then this is in lesson 35. So, nuclear fusion is something different from nuclear fission. Okay, so we're going to keep them separate. This is going to be the process of combining something smaller to make something larger. So, it's the opposite of nuclear fission. So, this says, based on the figure below, why is nuclear fusion possible? Which elements are commonly seen in fusion reactions? So the reason why is because we said that nuclear stability wise, binding energy wise, that iron was particularly stable. And that this was kind of like it is the peak. It's kind of hard to see that this is the peak of the curve because it's not a very clear peak. So the reason why is because smaller atoms to the left, I'm going to put this left in quotes because it's not really left on the periodic table, but it's left in this image. Left can readily combine to form larger atoms until iron 56. Okay, because that's kind of when the cost benefit of putting them together goes down. It's going to start costing more to combine things heavier than iron to make things heavier than iron. So smaller atoms best. Now, if we're looking at which ones are going to be the best, they're going to be the ones that are down here. And we really don't know exactly from this image which ones, but it's going to be the smallest elements. So hydrogen. Down here, that's deuterium, helium, and other small, Anderson, please don't jump on the couch. Other small elements. Those are the ones that are commonly seen in fusion reactions. Okay, so what makes fusion important is fusion is the energy process that creates stars' energy. So when we look back up at our sun, we don't see our sun like this per se because one, we would go blind. So this is an image taken through probably a telescope or a satellite, something like that, where we're not in danger of the UV radiation burning up our cones and rods in the back of our eye. And now the fuel in a star, like our sun, is hydrogen and deuterium. So this is hydrogen on the left plus deuterium on the right to create a helium-3 isotope. Then helium-3 isotopes combine to form helium molecule plus 2 protons. Then 2 protons can come together to form the deuteriums and a positron emission. So this is the fuel cycle in all stars. And if you know anything about our sun, it's that it is a huge provider of energy. In fact, we are so far away from our sun, but still the sun can power things like solar cells, solar panels, which can generate electricity. We know that the sun is important for life, and that's just a little bit of radiation that we see. It's enough to keep us warm, but not too warm. And so it is a huge fuel source. In fact, nuclear fusion is thought to be a better source of energy than nuclear fission, but it's much harder to recreate. So different sized stars undergo a variety of different fusion reactions. So small stars are only going to convert hydrogen to helium. Medium-sized stars like our sun are who once they get later in their life can convert helium into oxygen and carbon. And then very large stars that can take the carbon and oxygen and make them into a variety of other elements like neon, sodium, magnesium, sulfur, silicon, and then calcium, iron, nickel, chromium, copper, and others. When that star dies, because all stars are in this life cycle, believe it or not, and so when they use up all of their hydrogen fuel, they're basically going to run out of gas and die, just like your car would if you ran out of fuel. When the star dies and it becomes a supernova, these heavier elements that were formed up here and the ones that are heavier than iron can form. So they're kind of like our recycling center, because if you know anything about the elements on Earth, it's that there's a finite amount of each element. We can convert from one thing to another. There's processes that then reconvert it back. So like when we die, there's a decomposing process. When we breathe in and out, those are processes. Photosynthesis is a cycle, just like the water cycle, the nitrogen cycle, the phosphorus cycle. But one of the things that we really don't quite know is long term, if you run out of a particular element, like say we run out of technetium and we're using that for technology, we have to find something as a suitable replacement, because we don't simply have any more. We don't have a way to find more. We don't have the mining that we need. Or if it's gold or diamonds, we know that those resources are, we're not going to call them renewable because they're not renewing as fast as we're using them up, but they're also not resources that are quote unquote necessary for life, like water, fuel, energy, things like that. But these out in outer space, we know that when stars die, it essentially then allows for some of these heavier elements to be formed. And then, those are the elements that later go on to form things like planets, like our own. And not to say that a sun is going to create a planet, but that it's interesting that out in space we can see some of this chemical conversion happening. So the one thing that's important, and it may not be important just like as a test question, is that the different stars have different nuclear fusion reactions. Now, the ones that we want to try to recreate are pretty much going to be the smaller size stars. Smaller stars live longer. They're like fuel efficient, your Prius. Medium stars are like your SUVs, and then large stars are like your trucks, your F-350, Duramax, 8 miles to a gallon. And if you have one of those vehicles, I'm not saying anything about your vehicle. Just they're not very fuel efficient. You can put a lot of gas in the tank, but you're not going to get a lot of mileage per gallon as a Prius, which is like 40 miles to a gallon. So small stars tend to live a lot longer than big stars. Big stars die faster. And our star is medium, so it's got about an average lifespan. All right, so fusion reactions on Earth. So how is it possible, can we, let's say, is it possible to take this fusion reaction that we know provides a ton of energy, we know that it can then create elements that we might need more of, how can we make those happen on Earth? Well, so first of all, although hydrogen and deuterium are both present on Earth in very large amounts, I think it was a bird. I think a bird just crashed into the window behind me. That was loud. I think it was a bird, Anderson. It's okay. Oh, the apocalypse is happening. Okay, now calm down. Now he's going to lose it. Although hydrogen and deuterium are present on Earth in very large amounts, meaning there's not a supply issue, there are no fusion reactors currently in use. And so I will say that this was true whenever the text was printed. So I don't believe that is 100% true. I know like small scale fusion reactors are people are saying it's possible, but a large scale, fully, operational fusion reactor still has not happened. In fact, there is an organization, a group of countries that are working together to try to get one working, but their deadline just keeps getting pushed back further and further because there's material issues. So what are the problems, the technical problems preventing the use of fusion reactors? Okay, so what are the things that are making it difficult for these scientists? Well, the first is that there's a requirement of temperature that is very high. So fusion reactors require very high temperatures. And you can think about our sun as an example. So the problem with that is we just really don't have the materials that can house something that's reacting at that temperature. Things would melt. Things do melt. Things undergo reactions. Things become weakened at temperatures this hot. And so some of the problem is that they're trying to develop these materials at the same time that they're trying to build the reactor. And so they're finding out, okay, those particular rods don't withstand heat. Those particular rods don't withstand neutron bombardment. They contribute in a bad way. So that's one of the drawbacks. The second one is that they require, that is not how you spell require, very high pressures. So one thing that is true about the stars in this universe is that they are ignited. So all stars are born in a nebula, and that's where they stay as what's called protostars. But one of the things that happens when those stars are born is there's a strong gravitational collapse. And in that strong gravitational collapse moment, what happens is the gravity is so strong and so intense, the pressure is so high that it's enough to ignite the fuel inside the star. And that is going to be a hurdle to cross, because to put that kind of pressure on something for it to self-ignite is hard, because that pressure is not something that we currently have the full capacity to do, the technology to do, the materials to do. And so it's like a bomb, essentially, right? So a bomb calorimeter is a small explosion, and that's kind of what this is, but it could potentially be a really big explosion, okay? So these two things in themselves are very difficult to recreate in the lab setting. Anderson, please. I can't write when you're doing that. So they're difficult to recreate in a lab setting for safety reasons, material reasons. But there's another really big problem that they are facing right now, which is that they can get these things going, but they are not self-sustaining. And that's what sets the star apart, is that the star is self-sustaining. No one has to go up there and, like a pilot light, if you have a pilot light and you have grew up with natural gas, you know what a pilot light is. No one has to go up and light the pilot light every morning to make sure that the sun is going. And if the sun goes out, the sun goes out. There's no changing that. And so these fusion reactors have to be self-sustaining in order to be operable. And that's going to be a trick. That's going to be probably the long-term hurdle. I think we can recreate high temps. We can recreate high pressures. We have a lot of information about solid material science, which I love. This field of science is solid materials. But in order to make something self-sustaining, it means that these materials have to also be self-sustaining. And that's the part we don't really know. Long-term, are we building things that are strong enough? All right, so we are not going to talk about hydrogen bombs or atomic bombs, okay? They do not show up in your ACS test. I've never seen a question about a hydrogen bomb or atomic bomb, okay? So that's the end of lesson 36. We're going to do lesson 37, and then you guys will be all done.